Okay, so last hour of class, we talked about a lot of stuff, a lot of different types of numbers. We talked about that idea of a count and a name. So the question is, how does that become useful in all of our calculations? And again, I'm not trying to imply that you guys don't know how to add and subtract and multiply and divide whole numbers. But the process, especially for larger numbers, becomes easier to remember if you understand where it came from. So we've talked about this count and a name. How does that relate to our larger numbers? Well, the concept that ties it all together is the idea of place value. And I'm not going to dwell on place value a lot, but it is an extremely powerful concept. Just as powerful as the idea of a number when properly defined, as we said, those two parts of the count and the name. Place value is just as powerful, even though it is quite simple. Just a very quick review. If we start at our decimal point, or if we start at the end of the number and we work our way backwards, what's this first place value? The ones. Second place value? Tens, and then hundreds. And those are actually our three place values. That makes up what we call our base group. Then we have the thousands group. And in the thousands group, we have the same place values. Ones, tens, and hundreds. And then, of course, we have the millions group with the same place values. And if we were to name a place value, we name its place value and its group. For example, if I wanted to name the 8 here, that is in the 8. It's in the 1,000s place value. Or the 5 is just in the tens place value. Now those place values come into play in a lot of things. In their purest form, it probably comes into play in rounding. And we all know how to round. But if I say round, let's take this number right here, and I say round to the nearest 1,000. Of course, now you all know what that's going to come out to be. What's it going to be? 39,000. Perfect. And in a second, we'll come back to the process we use to do that, our shortcut. But let's look at how we really round. We all know the shortcut. We know how to get to 39,000, but what does it really mean? When we're asked to round to the nearest 1,000, what it's asking us to do is to look at our basic structure of those numerals, of those amounts. Our counts, the count portion of a number, the amounts, fall on a number line. They're defined on a number line. And when we're asking you to round to the nearest 1,000, what we're asking you to do is look at a number line that is labeled only to the nearest 1,000. And it's asking you if this number here were on that number line, which one would it be closest to? Well, 38,759 is somewhere in here. It is physically closest to or nearest to the 39,000. And we're asked to round. That is what it is telling us to do. Look at that number line. Identify the thousands on each side of that number. Which one is it nearest to? Now, of course, the way we tell it, our shortcut is we find the thousands place, which is the 8 in this place, the 8 1,000s, and we look at the next digit. Why do we look at the next digit? Well, that next digit tells us where we're at between these thousands. This 8 in the thousands place tells us we're between the 38 and the 39,000. This 7 right here tells us that we're at that point between them, that we're closer to the next one up. So we know that anything below 5 is closer to the 38. Anything bigger than 5 is closer to the 39. What do we do if it is exactly 5 in that digit? We round up. Why? Because somebody always told you if it's 5s always get rounded up, right? Well, if we look at it, this isn't just 38,000. Well, let's put an example out here. I'll do 37,000. Let's say we got 37,512. Well, 37,500 would be exactly in the middle, wouldn't it? But it isn't 37,500. It's 37,512. It's actually slightly past that. So the reason the 5s always get rounded up is because there's usually something that comes after the 5 that means we're slightly past that point. So it really is nearest to the next one up. The only problem there's really an issue is if, let's say it's just 37,500 exactly. Now it is exactly in the middle. For our purposes, we're still going to round it up because that's what you've been taught. There are some applications out there, some fields out there, like mechanical engineering and mechanical design, where you wouldn't want to round all of them up. Because if you have to deal with tolerances and round-off errors, it can become a problem. In the construction field, I mean, basically, if you're within 1/8 of an inch, you're considered to be dead on when you're doing houses and rough construction. For furniture work, you're trying to be within a 64th. But still, you do have a little bit of play. It's not like in machining where you have to be within a few thousandths. So the round-off errors aren't such a big deal in construction. But there is a process. I won't show you what it is, but there's a process out there where when you have 5 in that next digit and it's all zeros afterwards, where you round some of them up and some of them down. Like I said, I don't want to confuse you, so I'm not going to show it to you. But if you're curious, let me know and I'll show it to you. But for our purposes, anything that has a 5 in that next digit gets rounded up. So 37,000, the 5 in the next digit, 5 tells us we round up to 38. I'm not going to dwell on that because I'm sure you guys all know how to round. So we're going to skip ahead then. I wanted to mention the rounding because estimation is a big part of how I teach dealing with numbers. Let's take a look now at our 4 basic operations. We'll start out with addition. And remember, we talked about 4 inches plus 7 inches, becoming 11 inches. Because when we add numbers, we have to have the same name, which we do. And we combine the counts, the 4 and the 7 make 11, and we keep the same name. Well, if we look at larger numbers, like 274, you might look at that and think, I don't see a name. Well, there is a name there. There's actually more than one name there. It goes back to our place values. What we're used to seeing numbers written as, the 2, 7, and 4 here, is just an abbreviation of that whole number. When you were younger, you may have called it expanded form of a number. It's really just the full form of the number. The full form of that number, 274, looks like this. It is 2 hundreds and 7 tens and 4 ones. The place values are the names. So in fact, in a larger number like this, each digit is a count and a name, or the place value tells us its name. So then, let's say we're going to add that to something like 315. Well, 315 is going to be 3 hundreds and 1 10. Pretend you can actually read my writing. And 5 ones. Get rid of the S on the 10. There's only one of them. And when we're taught to add large numbers, what was the big thing that was stressed to us? We have to make sure we line up the columns, right? Got to make sure there's nice, neat little columns. Well, the question is why? What do we care about lining up the columns? Well, because when we add numbers, we can only combine things that have the same name. So I can only combine these 10s with these 10s. They have to be lined up so I can combine them. I can only combine the 1s with the 1s and the 100s with the 100s. And once they're lined up, I can go ahead and then combine them. I'm just adding straight down the column. So 200s and 300s make 500s. And 7 10s and 1 10 make 8 10s. And 4 1s and 5 1s make 9 1s. So we get 589. Now, some of you may have been watching carefully what I just did there, and you might be thinking to yourself, he did that backwards. How have we always been taught to add large numbers? Start at the end. Start at the right and work our way back to the left. Why?
Because if you get ones that end up more than 10,
Okay, and what do we call that process? Do you remember?
carrying over.
Carrying. In case we have to carry, we can run into numbers like this. And we're taught to start at the right, start at the end and work our way backwards. Because you run into 8 plus 9 is 17. We're going to keep the 7 and carry the 1. So now 1 and 7 is 8, plus 5 is 13. So we keep the 3 and carry the 1. 1 and 5 is 6, plus 2 is 8. We get 837. So we've always been taught to start at the right and work our way back to the left in case we have to carry. Now, I'm not going to tell you that's wrong. I'm just going to tell you that's not the only way to do it. There are actually, that's the most common algorithm or process for adding long numbers. Not the only one. The process of carrying is actually relatively new. Now, by relatively new, I mean less than 200 years old. It started in the mid-1800s when they started using carrying because it saves space. But there are actually several other ways to add numbers. One of the ways that you can add numbers, I'm going to use the same numbers here. So 578 plus 259. You just start on the left side. 5 plus 2 is 7. 7 plus 5 is 12, so it's 2, drop the 1. 8 and 9 is 17, so 7, drop the 1. You get the same answer. Now this takes a lot less space. Both of them are about the same speed. Maybe this one might take a little bit longer, but they both get the same answer. Now I'm making a couple of points there. One is that there isn't just one way to do it. We get so stuck in there's actually one right way to do things in math. There isn't. A lot of times there are several different processes. The second is I'm not going to force you to do things my way or a certain way. If I show you a way of doing something, like adding numbers, if I show you the standard way, and you happen to have a different way that you've always done or that you've tried and it works well for you, you remember it, it's easier for you, come and talk to me. I'll look at it and make sure it is something that does work every time, and I have no problem with you doing it a different way than what I do. There are different ways. Now, on the realism side of things here, I also realize that most of you own calculators, and hopefully shortly all of you will own calculators. And if I get 3-digit numbers to add, quite often you're not going to take the time to write it out by hand. You're going to probably punch it into the calculator. But I don't want you blindly punching numbers into a calculator, because if you're anything like me, I have these nice sausage fat fingers. I go to push numbers on the calculator, and of course this is a virtual calculator, but it's not uncommon for me to go try to punch in 578 plus 259. Yep, I did that on purpose. Is that the right answer? No, what happened? Well, yeah, it's 578, not 58. I went to push the key and it didn't register. Or sometimes I even do this, 578 plus 259. Come on in. So, of course, you can tell this one's not coming out right because my fat fingers, I hit an extra key, right? Sometimes if we're in a hurry and we're not paying close attention, those mistakes would get through. So what I usually ask you to do, if you're going to use the calculator, at least do this. 578, that's close to 600, right? 259, that's close to 300. 6 and 3 make 9. You keep the same name, that's 900. If I get an answer, 837, that's in the ballpark of 900. So when my calculator spits out 837, I know I'm at least not way off. I know I'm in the right ballpark. 317, I would have caught that. That's way too far off. 6,000, I definitely would have caught that by paying attention. You don't even necessarily have to write this out. Just look at, okay, 6 and 3, that's about 900. I better get an answer close to 900. So let's look at subtraction. Let's look at something like 675 minus 261. Now, I am not going to go ahead and I'm not going to write these out in the long form of 600s and 710s and 51s. I think you guys get the point now that you have to line up the columns. Addition and subtraction can only combine things that have the same names. So we've got our columns lined up here, 1s and 10s and 100s. We're ready to go. So we're just going to subtract down each column. 6 minus 2 is 4, 7 minus 6 is 1, 5 minus 4 is 4, or 5 minus 1 is 4. So we're at 414. What did I do again? We went left to right. We went backwards. What did I do again there? I went left to right. And we're used to going right to left. Why do we go right to left? In case we have to borrow. Carry. Borrowing is the subtraction equivalent of carry. So we might have 936 minus 287. We've been taught to start on the right and work our way back to the left because we run into this. 6 minus 7, of course, can't be done. So we're going to come up here and we're going to borrow from the 3 and make that a 2. This now is a 16. So 16 minus 7 is 9. 2 minus 8 can't be done. So we're going to borrow from the 9. This is going to be an 8, and this is now a 12. 12 minus 8 is 4. 8 minus 2, 6. So we have 649. And that's typically the way most of you have seen the subtraction done. Now, as I mentioned with the addition, there is not just one way to do subtraction. I could start like this. 9 minus 2 is 7. 3 minus 8 can't be done, so I'm going to borrow from the 7. That's a 6. This is a 13. 13 minus 8 is 5. 6 minus 7 can't be done. I'm going to borrow from the 5. That's a 4. This is now a 16. 16 minus 7 is 9. I get the same answer. Technically, when we're borrowing, we're not really taking from this top number up here. What we're really taking from is the answer for the result from the previous column. But, of course, this process works every time, and it's a little bit shorter and quicker. But again, the point is there isn't just one way to do things. There's multiple different ways that will always work out. And again, as I mentioned before, I don't expect that a lot of you are going to sit down and do a lot of long subtraction by hand because we have calculators. Now, I'm not saying that it's not worth your time to be able to do it by hand. It really is. I used to do a lot of work on job sites, and I would throw my calculator in the windshield of my car or in the dashboard of my car or truck, and I'd get there, and what happens to stuff like that when it sits in the sun in your dashboard too long? Yeah, it gets baked. And sometimes it would be visibly okay, but the circuits inside were fried and it didn't work. Or the screen had burst and it was all black. Or there were a couple of times it actually wrinkled right up because it got hot enough that it actually warped the plastic in it. So you get there and your calculator doesn't work, and you do still have to function sometimes without it. Especially in construction. You got sand and all that stuff. It really isn't necessarily practical to have a calculator strapped to your hip all the time. So being able to do some of these calculations by hand is really useful. But as I said, I know that the calculators are there and that many of you will use it. So let's take a look. If I were looking at this before I punched it into the calculator, I would at least say, okay, this is about 900. This is about 300. Again, we're going to do 9 minus 3 is 6. Hundreds and hundreds stays hundreds. It's 600. So I know that I'm expecting my calculator to spit out an answer in the ballpark of 600. Make sense? Okay, well, let's take a look at multiplication. Long multiplication, most people have it down, but there's still a lot of room for mistakes. And let's look at something like 23 times 31. This one I am going to go ahead and write it out in its long form, in its full form. So 23 is 2 tens and 3 ones. 31 is 3 tens and 1 1. When we multiply, do we need the same name? No, we don't. So this 2 tens here not only can combine with the 3 tens, but it can also combine with the 1, 1. The 1 1s here can combine with these 1s, but it can also combine with these 10s. In fact, every digit of one number can combine with every digit of the other number. So our process of long multiplication is nothing more than an organized way of making sure that every digit in this number gets combined with every digit in the other number. So we usually start out with the last digit of one of the numbers, and I've always been taught to start from the bottom number. Some people are taught to start with the top number, but I'm going to go the standard way. I start with the last digit of the bottom number, the 1, 1. And I'm going to combine it with the 3 1s. And just like before, we combine the counts. 1 times 3 is 3, but we also combine the names. 1s times 1s is 1s. And then I'm going to combine it with the next digit in the top number. 1, 1 times 2 10s. Again, 1 times 2 is 2. 1s times 10s is 10s. Now when we move to the next digit here, what have we always been taught to do down here? Either leave a 0 or leave a blank space there and move over a spot, right? This next step is going to explain why. So now we're starting out with the 3 10s. Times 3 1s, what's 3 times 3? 9. But 10s times 1s is 10s. Putting this 0 over here, all that did is it helped us keep our 10s lined up together so that our place values stay together. And now we have 3 10s times 2 10s. 3 times 2 is 6. 10s times 10s is hundreds. So that had to slide over there into a place by itself. So we've got 3 and 0 is 3, 2 and 9 is 11, so 1 greater than 1, and 713. Now I'm not going to go through and do a bunch of examples along multiplication, but I think you get the point. Those place values and the fact that when we multiply we do not have to have the same name explain why we do the long multiplication process we do. And again, I realize you have calculators, and when you get into a couple of digits like this, you're probably going to punch them in. But I would at least expect you to look at this and say, okay, 23 is really close to 20. 31 is close to 30. Now the estimating here is just a little bit different. We do 2 times 3 is 6, but this is 10s times 10s, which is hundreds. Does anybody know the shortcut for multiplying rounded numbers like that? Yeah, 1, there you go. You got 1, 2 zeros, you're going to have 2 zeros added onto the end here. So if I were estimating and I had something like 4,000 times 20, well, I'm going to do the 4 times 2 is 8, then 1, 2, 3, 4 zeros. Where'd that really come from? Well, this is thousands and this is tens. Thousands times tens makes 10,000. So the 8 has to go in the 10,000s place. So anyway, enough of that. One last operation to go, and then we're going to give you some time to work on your homework a little bit. The last operation, of course, is division. But before I talk about division, I want to just take a little bit of a closer look at the definition of multiplication. We jumped into the long multiplication, but we didn't really look at the single digit stuff. What happens with these single amounts? Back in first grade or so, when you first learned how to multiply, before you memorized your tables and you knew that 5 times 3 had to be 15, what would you do to try to figure out 5 times 3? Count up by 5s, or just do 5 plus 5 plus 5, right? Repeated addition. 5 times 3 just means 3 5s added together, giving us the 15. Now I've said a couple of times that division is just multiplication done in reverse, and that they follow the same rules. So if multiplication is repeated addition, division is repeated subtraction. 24 divided by 8 is asking us, if I take 24, how many times can I subtract 8 from it? So 24 minus 8 is 16, that's once. 16 minus 8 is 8, that's twice. 8 minus 8 is 0, that is 3 times. 24 divided by 8 is 3 because I can subtract 8 from 24 3 times. And even when we have remainders, it's the same process. Let's say we have, oh, what do I want to do here? 27 divided by 6. 27 minus 6 is 21, that's once. Minus another 6 is 15, that's twice. Minus another 6. 9, that's 3 times. And minus 6 again is 3. That is 4 times. Can I subtract 6 again? No. So 24 divided by 6 is 4 with a remainder of 3, or 3 left over. Now, we'll get into converting those into decimals or fractions and stuff like that. But for now, that whole idea of a remainder, that's what it is. That's how much is left over after you subtracted it as many times as you could. So with that thought in mind, let's look at long division and see where on earth long division comes from. Let's take something like 69,273 and let's divide it by 21. Now, we just said that division is repeated subtraction. Well, I am not about to start subtracting 21 from 69,273. I don't have that kind of free time, and hopefully you don't either. But what I can do is I can subtract the 21 in big chunks. Like if I could subtract 100 of the 21s or 1,000 of the 21s or whatever. And that's exactly what long division is it's a way of subtracting that number in large chunks. And the way it was done, now this is not going to look much like what you have learned for long division. I'm going to warn you that right now. And I don't expect you to change how you do it. I'm just showing you where things came from. So the way it worked is you look at what's the place value of this first digit here. 10,000. So if we try that place value, 10,000 times 21 is 210,000. Can I subtract that from this? No, I cannot. So the next place value would be 1,000. So let's try 1,000 times 21. So 1,021s is 21,000. Can I subtract that? You bet I can. Can I subtract it more than once? Yes, I can. In fact, I can subtract it 3 times. That would be 63,000. That would leave me with 6,273. So what I really did I subtracted 21,000 3 times. What I really did was I subtracted 1,021s 3 times, or I just subtracted 3,021s. Does that make sense? So what's my next place value? After thousands, it would be hundreds. 100 times 21 is 2,100. Can I subtract that? Yep. Not quite 3 times, right? Just twice. That's going to be 4,200, which is going to give me 2,073. But how many times did I just subtract the 21? 100 times 2, or 200. So I just subtracted 200 more 21s. Next place value? 10s. 10 times 21 is 210. I can subtract that. It looks like 9 times. Get 183 left over. Again, how many times did I just subtract 21 here? 10 times 9, or 90 times. And finally, I'm just subtracting 21. How many times does 21 go into? 21 times 21 is 21. That would be times, will it go 9? Not quite. We'll only go 8. 168. There's 15 left over. So I just subtracted it 8 more times. 8 times 1 is 8. So I have 3,298 with a remainder of, we had 15 left over. That's my long division. Now, to be honest, this is messy and it's long. It's really long and tedious. But this makes sense to me, where you're just subtracting it repeatedly, just in large chunks. But you might be looking at it thinking, that looks absolutely nothing like what I was taught for long division. Well, in reality, it is not as far away as you think. It really is the same process, just severely abbreviated. What we were taught is you take the 21. Okay, does 21 go into 6? No. The 10,000 21s could not be subtracted, so we couldn't subtract those. How about 69? Yeah, 21 goes into 69 3 times. That would be 63. What we just did there is we moved down to the thousands digit. Notice here we have the 3 here, the 63 here. All we did was leave off a whole bunch of zeros there. We subtract, we got 6 here, and then we start bringing down digits. Now for me, I usually bring down the whole rest of the number and just keep track. This is the digit I'm working on right now. So does 21 go into 62? Yeah, it goes twice, and we keep going. And you'll notice the process is very, very similar. Many of the steps look identical. Most of the steps are identical, just with zeros missing. Now, once again, I realize not going to do a lot of long division. To be honest, long division is the one operation I avoid doing in my head or by hand if I can. That's the one time I'll pull out the calculator and use it. So what would we do to help our estimate here? Well, this is about 70,000. This is about 20. Now, of course, 7 doesn't divide by 2, does it? But 70,000 divided by 20 is going to come out to be roughly 3,500. I'll show you how I did that estimate in just a second. When our calculator pulls out 3,298 point something, technically what would that be? 0.714285714.3 approximately. We know we're right. Don't worry, it's not contagious. One of the reasons I'm showing you this stuff is there are patterns behind your calculations. The reason I can take something like that, I can take a number like 69,273 divided by 21, and I can give you that is 3,298 point, not 5, point 714285714.3 approximately. You can punch in your calculator and double check me if you want to. The only reason that's a 3 is because I rounded it off. There are patterns. Once you start seeing the patterns when you calculate, the calculations are easy. But you can't see the patterns unless you know what's really going on behind the scenes like this. So anyway, let's talk a little bit about estimating with that division. When we were multiplying, we had like 30,000 times 200. 3 times 2 is 6. How many zeros? 1, 2, 3, 4, 5, 6, right? Not so bad. When we're dividing, we're still going to divide the numbers. What's 8 divided by 2? 4. But now instead of combining the zeros, we're going to cancel the zeros. Yeah. So we cancel off those zeros. We got 1, 2 zeros left. Now the example I did up here was 70,000 divided by 20. Here, 7 doesn't divide by 2, does it? But I can steal that first zero. What's 70 divided by 2? 35. Now I only have 3 zeros to work with here. I cancel 1 and there's 2 left. 3,500. Any questions? See, this estimating here is a big deal. I will catch it, most of you at some point in the semester, punching something in your calculator and writing down the answer and not catching that something got entered wrong and it's off. So make sure you don't necessarily have to write things out, but make sure you're looking at getting that idea in your head before you start punching anything in the calculator. Okay, so for right now, we have about 20 minutes left in our class period. I'm going to give you that time to start working. And I do ask that you start working. If you don't have your textbook, look on with somebody next to you for right now. We're going to be working out of the little book. It's the one that says Practical Problems in Mathematics for Carpenters. And in that little book, we're actually going to be doing units 1, 2, 3, and 4. Now, I realize that's a lot of problems, but we did some pretty basic stuff today. Now, in those units, I don't expect you to do every problem. I'm asking you to do the odd-numbered problems, 1, 3, 5, 7, 9, and so on. There will be some where you run into there where several problems deal with the same drawing, and you may have to go back and do some of the even problems just so you can do the odds. There's two reasons why I'd have you just do the odd problems. One is I don't want you to sit here and do 50 or 60 problems a night. The second is, if you look at the back of the book, the answers for the odd-numbered problems are in the back of the book. At least what the textbook publisher feels are the answers. There will be at least a few of them in this textbook that we'll catch that the answers are wrong in back. And so if you hit one and you're stumped and you've done it a few times and you just can't make it work out, we'll start out class tomorrow by answering those questions of, are you sure the book has the answer right here? Or, on this one, I couldn't figure it out. Can you show me how to do it? But anyway, make sure that you check your answers in back. I'd suggest you do a few and check them to make sure you're on the right path. And as I said, when you come in tomorrow, I will not ask you to hand in your homework for a grade. I don't have that kind of time. But as I said, I might have a problem up on the board for you to do when you come in to sit down, work on it while I'm getting ready for class or whatever. It might take me a minute or two sometimes to get ready for class. Work on that problem, and there may be some days I say, hey, you know what, hand in that problem so I can see what you did. So make sure you're doing it on a separate sheet. Right now I'm going to shut up and I'm going to give you 5 minutes to get started working or so, and then we might start working at some of the problems ourselves. If anything comes up, by the way, that you get stumped on or you're not quite sure what to do, just give me a yell and we'll do that one too to get you going.